you for coming to this last session. I know it was like last day, a long day, and I might want to also hit the whole road home. But I hope this is an interesting subject. And so we're talking about the benchmarks today, and in particular for messaging systems. And first of all, my name is Matteo Merli. I'm CTO in Stream Native, and I'm one of the creator of Apache Pulsar, and I'm the PMC chair as well. From Stream Native, and we have services based on top of Apache Pulsar, managed services, and all kinds of different options to run Pulsar. And we are also doing Pulsar Summit in next month. So if you are local, it is in San Francisco. You can just scan the QR code or talk to me, and we can give you all the information about Pulsar Summit. And so the first question is, why benchmark? Why people are interested in benchmarks, and why should you read benchmark, and why should you run benchmark and reproduce results? The first reason is that everyone loves the clickbait. Even if you don't trust 100% who's doing the benchmark, people will click on it and read it and comment it, and which is bad, but it's also good because it kind of forces people to think about these performance issues and how they apply to cost and to differences in the design of the different systems. The other thing is that trying to reproduce a benchmark is a good exercise because it gives you a lot of understanding on how system behaves, how system reacts to different conditions, and what are the limits, which is important. And especially as a user, you can use these tools to validate what your use case will look like. And you might do an estimate. For example, like if you have a 10 gigabytes per second use case, you might not want to set up a whole cluster and do a 10 gigabytes. You might want to do a 1 gigabyte and validate that on a smaller scale cluster. Everything looks fine, at least as a first step validation, and gather like all the information for lower cost. And you can also use that as a tool to refine the configuration or the setups and make sure that everything works as you think it would do, because in many cases it does not. Apart from users, is this kind of benchmarks and toolings, it also helps a lot developers. When you're developing a system, you're making changes and you want to make sure that the performance does not regress. You want to make sure you're moving in the right direction, and you want to make sure that you can simulate some particular workloads, some particular use case that the customers might have, and that you try to kind of like simulate to see the same behavior that they're seeing in their own environment. And for this, they're very useful as stress test tools. The same load generation typically applies for both conditions. Since we say that, okay, we were talking about messaging benchmark, and database benchmark has been around for a long time, so why cannot you use database benchmark to test messaging systems? There are many different reasons, but so database benchmark has been around for decades, 30, 40 years, and the industry has created a standardized version of relational database tests like TPC. There are 10 different versions of TPC with very specific workloads, very specific dataset sizes, and very specific queries, and everybody has agreed on this common set of workloads. For NoSQL, there's been not like a consortium that produces a standard like TPC, but YCSB, the Yahoo Cloud Serving benchmark, has been the de facto standard. Basically, every new key value store has been implementing YCSB driver and to measure the performance of the new system. Now, but YCSB focuses really on key value, like writes, reads on the key values, and you can play with the percentage of writes and reads and have different patterns there, like 80% writes or 20% reads or 50-50 and so on. Why is this testing messaging is different? Main thing is that the interaction between clients and the messaging brokers are not just like an RPC. typically you have sessions that are created, and then you pipeline data into these sessions. And so it's not just a simple one RPC. The difference between write and read is bigger. The other part is that performance in messaging typically is achieved through batching and pipelining. So clients, the SDK will basically always try to pack up a bunch of events into a single batch and then send it out in one shot to the brokers to have more performance. And apart from there is also that YCSB and others are really based on synchronous API calls, which basically kills the whole thing about batching and pipelining. And even if you take this RPC model out of the picture, there are still like different concepts that are different messaging. So one big task of a messaging system is to build backlog. In case your customers are down, you want to keep the data for a while, act as a buffer for durable buffer, and then drain that data accumulated. Now that doesn't really apply to a database test. Also, there are kind of like things like trying to discover what is the max sustainable throughput of a system. Again, it is very, very different. And then we have like things like fan in and fan out. Like many producers funneling into one topic, or having fan out of like one copy goes in and many copies of data goes out, as in like a broadcast model. So several years ago, we started with trying to create a benchmark for our own use, and then we figured out that, okay, there's no good solution out there, so let's build a framework, and we donated this to the Linux Foundation and the OpenMessaging project. The good part of that is that because of this vendor-neutral location, it has been able to attract other systems, other vendors that have been adding their own drivers for the OpenMessaging benchmark. But the goals for this project were really around to build a framework that you can have repeatable tests of messaging technologies. And repeatable is very important. That has to be vendor agnostic with pluggable drivers for a wide range of different systems. And it is really built with the core as a distributed load generator, and you can model your own use cases, and there are automated deployment scripts. I say that repeatable tests are very important. This is critical because once you see someone that publishes that claim that, okay, system X is 3 times faster than system Y, and you say, okay, is it true? I mean, I see the chart. It's nice looking chart, but first of all, like, is it really true? Can I run it? And it's important for users to be able to go into the repository, run a script, deploy in AWS, and be able to see with their own eyes the results and provide their own assessment on the validity of those results. And this is important for users. It's important for also other vendors that can say, okay, this configuration is not ideal. I want you should be tune this configuration and have better performance. But basically, yeah, the repeatability is really without repeatability, there's no meaning in any benchmark, right? So we say that we support many drivers, and these drivers have been all added and tuned by their own developers, their own vendors. So there's Pulsar, Kafka, so there's a bunch of them, and everyone is welcome to add more and more to this to the system. So it is the plugin API is very agnostic of any system idiosyncrasy. So it's very hard to add very different systems here. The architecture. So I say that it is the core of the system is a distributed load generator. That means that these workers get deployed on multiple nodes, multiple VMs in this case, and there is a single coordinator. The coordinator basically takes a workload definition and say that I have to generate this amount of traffic, and then measure the conditions that are on the messaging system. The workers are divided into producers and consumers. And basically, they specialize at this point, but the coordinator basically divides all the entire workload set into chunks for each worker. And the producer worker will start sending data, consumer worker will connect and consume that data. And the coordinator basically acts as just a controller. It will tell every worker what he has to do, and it will poll periodically every 10 seconds to fetch all the stats. And like the current throughput, the current lag, and so on. And then at the end, we just give you a JSON file with a result, overall result for the test run. With this JSON, you can build charts and whatever you want. The other part I mentioned is automated deployment. So again, to have an easy, repeatable test, you need to have a user that can just run a script. So each driver, basically, there are Terraform and Ansible scripts, and it basically runs on bare-bone VMs. And the VM times is the same, so try to be as apple-to-apple comparison as possible. And but you can modify those scripts, like if you want to test on a VM type, for example, that is closer to your deployment production, then it's very easy to do. There is also like a way to configure drivers. So there's a config file that basically each driver will have a different config file here, but basically it's just a YAML file where you can specify any particular setting that you want to tweak in the driver. Like for example, like on process side, you can configure how many copies of data do you want. If you want to have the exactly one semantics enabled, on the producer side, the batching parameters, and so on. One interesting part is how can user model their own use cases. And ideally, like you might have one use case which has some particular set of conditions, and it should be easy to match these on the load generator. And this is like very useful to validate the system behavior. So you can just instead of like try to have a prototype of your application and integrate with the system and then try it out at a scale, it can be very time consuming. But just doing a pre-validation check with this load generator can save a lot of time. And there are also like we have a lot of like general use cases. So these are more like trying to get a general pattern of messaging use cases and trying to abstract it a bit. And as in that, for example, like typical use case is one topic, one partition. This is just to show, okay, what is the upper bound for one partition, for example. And again, it might not be a super concrete use case, but it gives a lot of insight on the behavior of systems, because if you need total ordering, that's what you have to. That's your max, right? That's your max throughput there. Or one topic 100 partition. This is more like, okay, what is the if I have a decent number of partitions, what is the throughput and latency and so on. Or like testing with the right number of topics and see the different conditions changing depending on the number of topics. There are also another class of workloads which are more like a queue model based. Like for example, like if you have one topic, one partition, but with many consumers. No, Kafka cannot support this, at least for now. But other systems like Pulsar, RabbitMQ, and ActiveMQ, and so on, they will support it. So we have tested a lot of these, either one topic, one partition, or variety number of topics as well. And this is, for example, like how you define a workload. So this is like a very simple scenario. You do have define, okay, how many topics do you want to use, how many partitions per each topic. If you want to use a key distributor or not, basically no key will basically have, messages will have no key attached, but you can also have a distribution on some key cardinality that you can configure. Message size with some payload examples, and how many subscription per topic. If you increase that, basically it will mean that you're doing fan out and dispatching multiple copies of the data for each 1x out and say 3x out. Consumer per subscription, basically increasing that will enable more a queue style model. And producer per topic, again, if you want to test funny, it is easy to increase this. And in this case, there is a fixed producer rate and consumer backlog size. So the consumer backlog size is allowing you to generate a lag, an artificial lag, like simulating that I'm publishing some data, the consumers are down, they're not consuming for a while, and in this case, for say, you can say for like 1 terabyte or 2 terabyte, and then bring up the consumer and let them drain, and measure the system performance during that drain period, and finally the test duration. Now, another interesting example here is with producer rate 0. That means to discover the max sustainable rate, which I will get in a bit more. And again, yes, so walk like scenario, I can increase my consumer per subscription. It will just have round robin dispatching on the same topic. The next question, okay, we decided that, okay, why do we need it? What a workload looks like, and now, okay, when we do run this workload, what should we look at? What is important to measure? And I think there are 3 different dimensions that are typically important for users of messaging systems. So the first one is max throughput. If you have like a large volume use case, the throughput is directly correlated to the cost. Like if you want to do like a 10 gigabytes per second, you can just try 1 gigabyte. Okay, it takes 7 nodes, fine. I need 70 to do 10, right? That's typically very easy. That's at least the ideal condition. So if a system can give you like a 20% difference in performance, now that's 70 is like is 7 nodes. So it is not irrelevant as a cost difference. Now, if your load is not that high, that probably doesn't matter much. But for some use cases, it is very important. The other part is that the max throughput gives you an idea on upper bounds. You say, okay, with this cluster size, I can't do as much as this. At least you get some real-world upper bound given this particular configuration. The other dimension is latency. And the same producer latency. In most cases, that's the most important metric to look at. That's because when a producer application sends data to messaging system, it can say, okay, I hand it off. Now I can forget about this. That's not my job anymore. But in many cases, you have a user waiting for that acknowledgement to come back. So it is very critical that a messaging system it is able to accept a message under all conditions with low latency. Again, for some use cases, not for everything. But end-to-end tends to be less important because there are multiple other things that are involved there. Now, you may have like a late consumers, you may have different styles on how to consume the data. So end-to-end is generally less important, but producer latency is in many cases very critical. And the third one is the same metrics, but tested under different conditions. For example, what happens to throughput and latency if one node goes down? Or what happens if there is a backlog draining scenario and with catch-up reads from disk instead of memory? And okay, how does this affect the throughput and latency? And we talk about, okay, how to measure throughput. The key here is the max sustainable throughput, right? It doesn't matter like if a system can accept writes, but is not able to dispatch the reads. So even if it can take 2 gigabytes per second, but your consumers are not able to because they're starved, that's meaningless, right? We need to basically detect what is the right level of throughput that we can increase on the producer side that the consumers are able to keep up. So once we tip the point, then we have to step back. Essentially, it is like a feedback loop here. And there are basically like 2 different metrics that we look at. One is that we increase the throughput and the backlog increases. Basically, consumers are falling behind. That means that we went too high, so we have to step down. The other part is that when there is back pressure. So if we see back pressure, that means that producers basically are are getting back pressure, that means that we are also too high, right? We set the rate too high, so we have to step down. So basically, it is a bit of an iterative process, and but in general, it does converge into a single, a stable rate. And basically, we tweak the producer, and then we keep checking the consumption rate, back pressure, and then we tweak it. If it's too low, we can try to step up. If it's too high, we step down, and then it generally converges. So this is just one example of testing with, again, this is fault-tolerant Kafka, but it kind of give you the idea of the output of the benchmark around testing on a single partition and single topic, single partition. And again, this is all with the recommended setup from each developers. On the latency side, so latency typically, like, you want to not run at the very top, at the max rate, but you want to step down a bit. So you typically, like, when compared to system, we run at the same rate. So you fix the rate, and then you measure the latency on the system. Like in this case, the rate was fixed at 500K per second on one topic, 100 partitions, and then measuring the latency. And these are latency profiles. So what is interesting typically is to see the progression of the latency quantiles. On the left hand, you have the P50, the median, and on the very right, there's the max, and in between, there's like the P99, P99.9, and P99.49 here, right? But it is important to see how the progression goes up. And the lower the profile, of course, the better, because it means that the latency is stable for statistically more events than other. Like if it breaks down at the 99, it means that 1% of your events are going to be having higher latency. So if you have users clicking on your page, they might experience 1 out of 100 higher latencies, and they get the performance. Another important part, which is often omitted, is a coordinated omission. It's a bit counterintuitive to get, but you can think a bit of that. Like in general, like all these systems, we use async APIs because the SDK will take care of the batching and so on, right? So you typically do like a send async, and then there's a callback that comes back, and when the message is persisted. Now, an async call in the SDK, in many cases, doesn't mean that it's not blocking. It can block under certain condition. And there are multiple reasons why either the thread is maxed out, or the local buffer is full, so you have to apply back pressure. There are a bunch, or there is some inefficiency in the client library and so on. For all these conditions, basically, you call this async method, which is not a zero time. It can take milliseconds, or tens of milliseconds, or hundreds of milliseconds even if it is called async. If you're not careful, if you just do a loop, okay, I measure the time before I try, I measure the time when the message is published, you're missing the fact that the first message can delay the next one. So one example is that you're trying to publish 1K message per second, okay, but now the SDK that's trying to produce, it is blocked for more than 1 millisecond. That means that the second message, the thread is blocked, so we send the next message not at the 1 millisecond mark, maybe at the 3 millisecond mark. So that means that for 3 milliseconds we were not able to publish anything. So, but then if you just measure the latency, that the second message latency, maybe it is low, but the fact that you are blocked, you should be accounting for that. So that it is important, because otherwise it is very easy to not seeing that back pressure getting applied, and the effect that you are effectively delaying everything, and you should be measuring that. And most measuring systems are not accounting for this. So we talk about failure scenario, and this is also where things get very interesting, because So first of all, when we started Portstar at Yahoo, before Portstar, we were working on all the messaging system, and we had like one time a big incident where we were like not able to consume data for extended amount of time. And we were saying, okay, fine, we have disk space, we can store the data. We can add more disk space. It was not easy, it was operationally involved because it was not just adding more storage, but we get to swap out all these NFS servers and so on. The problem was that even when we put the consumer back online, the problem was that we had a whole many tens of terabytes or hundreds of terabytes of data stored, but we didn't have the I/O bandwidth to read it out. So it was useless. So it doesn't matter if you can store data, if you cannot replay it out. At the end, you have to drop it if you cannot replay it. And because when you replay, you also have to account for the fact that you have to keep accepting new writes. And the writes will not stop because the writes are generated by user events. So all this to say is that it's important to simulate this consumer backlog catch-up read scenario. And in any use case, I would recommend people to test this out because that's part of the sizing of the system. And honestly, like handling late consumer catching up is one of the most important tasks of a messaging system. And it's in general like one of the least understood. People tend to think that, okay, I can put messages in the queue and I will always be able to read it out. But ideally, like if you have to put a goal on this, is that you want to be able to drain the backlog at twice the speed. At the same time, you don't want to impact the write. And by impact, there should be no impact on the processor throughput, and there should be no impact on the processor latency. So with this workload, with the consumer backlog, we can simulate these consumers going down, stopping the dispatch rate to 0 for a while, building X amount of gigabytes of backlog to catch up, and then bringing them back online and try to drain as fast as possible. So this is one example. Again, this is Portstar, and the black line is Kafka. And this is what happens when the consumers are brought back online. So the higher the better means that Portstar is able to drain this backlog faster and sooner. And well, it's like 1.5x difference here. So this is like the drain throughput. Of course, you want to have it faster so that you can resolve the issue sooner. The more important part, though, is the latency. For example, like the black line here is Kafka. So whenever this draining is happening, the latency shoots up to hundreds of milliseconds. This is like 300. So this is the P99, and it shoots up to 300 milliseconds or 1 second even on the processor side. That also comes from the way that Kafka does on the uses mmap on the files and access the thing. So latency is fine when the reads are coming from memory. When you're falling behind and you're outside, your data set is bigger than your RAM, it has to basically fetch from disk. Now they are called disk reads, and whenever a producer is trying to use again the mmap to access and write memory, the consumer is swapping this page out, and it will be basically causing a page fault on the producer. Now, before it was memory access, now it is like 200 milliseconds disk read. A similar example, so this is like comparing with RabbitMQ, for example. You can see in this case, it is the throughput. So if you see that on the light blue shadow on Portstar side, it is when the draining is happening. There is no impact on the throughput at all. It is stable. We set it to 100K. It is stable to 100K. There is no impact there. On the RabbitMQ side is the orange shadow. It is when the draining is happening. So here the throughput was set to 30K. That was about the max that RabbitMQ was able to reach anyway. And when the draining is happening, basically it tanks the throughput. So the producers are getting pushed back. They cannot publish anymore. It is very bumpy and so on. And only after it gets resolved, then it goes back on memory. place, then it is able to go faster. But there is a huge impact. So basically, like if you use these systems on an online service, whenever some of your consumer is down and then catches up, if you have a huge impact on your online services. So that is definitely something I would recommend to test in any system you're trying out. Simulating node failure. I haven't filled up this one, but I would recommend as well to try with different kind of like node failure scenarios, trying to kill nodes, trying to simulate network partitions, try to take network down and see what is the impact. How much time it takes for the system to recover from there, and is it like a 2 seconds latency bump, or is it like a 10 minutes downtime? That is also like a very, very different scenario. And to conclude here, I would say that simulating all this kind of scenario is very important. And as a user, I would always recommend to do a scale test or a stress test when you're evaluating a new platform. And it is really important to try to model your use case. Start with your use case and try to model it close as possible and see what kind of system is the best suited for your use case. And then try to also expand and test out with more general use cases that you might have not today, but maybe down the road. And that may be important later on. It is also a very useful exercise that helps a lot of users to understand the internal behavior of a system and what are the limitations of the platform. And because you cannot just treat systems as black boxes. I mean, ideally, yes. You should be able to say, okay, I can put anything on this platform and it will take it. The reality is that every system has different breaking points, have different breaking scenarios, and has different limitations and different trade-offs. And they might or not affect you and your use case. Finally, it's also very important, and I think one of the most important sections in all the published benchmarks by vendors or by practitioners is really understanding the why. Why there are these differences? Why am I seeing this latency difference? Why am I seeing this throughput difference? What does that mean? Why is system X able to have lower latency than other? There's always a reason. Sometimes it's a design reason, sometimes architecture, sometimes is different trade-offs, different optimization. Sometimes is bad configuration, and that can be easily fixed, right? It's important to understand what is the bottleneck, why is the reason for both latency and throughput limitation. And also, honestly, it's also important to get, even if you're testing one system, it's important to ask the question, why is the limit here? Why is here not lower, not higher? And what am I saturating? Is it a CPU bound? Is it IO bound? Am I maxing out the disk? Am I maxing out the CPU? Am I maxing out on, say, one single core? For example, there can be many cases in which everything gets mixed up into one single thread, and you're maxing out one core, even though you have many CPUs. But it is typically very important to understand this, because without, you can just throw hardware, but it does not improve the performance. And finally, the understanding what is the impact of any, and what are the trade-off for different settings and options. So all the systems, they have tens or hundreds of different configurations, different ways of setting buffers, setting limits here and there, and changing one of them will impact your performance. But it might improve it in one sense and make it worse in one other sense. For example, like you may increase throughput on one side, but make latency worse, for example. So you should be testing all these different conditions. And this was all. So thank you. And if you have any questions, or if you have any other comments on benchmark, I'm happy to chat about it. Thanks.